Good day, everyone. My name is Lawrence A. Cornelio, ABS EC3 student from Bicol University, Palongi, and today I will be discussing about IIR filters. So let's proceed to the code. So first, we import the matplotlib, and we import numpy. Then we import CP, CP signal, butter, frec, C, and ifilter. Then from CP, we import FFT. Now, first, we create the input signal. So we set our sampling rate to 1000 hertz. Then our time vector goes from 1 second over our input signal, which is 1000. So then we create a clean 5 hertz sine wave. So we create a low frequency sine wave. Then we create the high frequency interference at 200 hertz with half, half amplitude and add random noise. So when the noisy signal is the sum of all three, so this 500 hertz signal is what we want to keep, and the 200 hertz plus random noise is what we want to remove. Now we plot the noisy signal, so we plot the noisy signal here, one. Now that's on the code, so we can see the noisy signal. So this is the noisy signal. Now we design the IIR Butterworth filter. So we set our cutoff frequency to 100. So when we choose the filter order is equal to 4, the order determines how sharp the filter is. Higher order gives us steeper cutoff but more computation. The butter function designs the filter. Then IIR gives both numerator B and denominator A coefficient because of the feedback. Then we use Frex to compute the frequency response. At low frequency below 100, the magnitude is close to 1, meaning those frequencies pass through at 100 Hz, the magnitude drops. At 200 and above, the magnitude is near 0. This confirms our low pass filter works as expected. So now we run, so let's see the plot. So here, this is the frequency response. So at 0, 1, and near 200 is 0. Now, so we create a we then now use ifilter with both numerator coefficient B and denominator coefficient A to apply the IIR filter. So the denominator coefficient represents feedback. Now we compare the comparing noisy and filtered signals in the time domain. So here, the so the top tablet shows the original noisy signal. So you can see rapid fluctuation from high frequency noise. And the bottom subplot shows the filtered signal. Notice how much smoother it is. The 200 Hz component has been removed and the random noise is significantly reduced. The clean 500 Hz sine wave is now clearly visible. So this proves our IIR filter successful clean signal. And now we look at the frequency domain using FFT. So now the plot. So the top subplot show the spectrum of the noisy signal. You can see clearly a large peak at 50 Hz, a smaller peak at 200 from the rest, and a noise floor across all the frequencies. The bottom subplot shows the spectrum after filtering. So the 200 peak is almost gone here, dropping significantly, but the 50 Hz peak remains strong. So this confirms the filter removes the high frequency while preserving the low frequency we wanted. So that's all. Thank you.